Now we're recording. Everybody good with that whole first problem that we did? Yeah. Yeah. Okay. That's good to show it all the way. All right, so what we did, I'm just going to repeat real quick since I forgot to record. We said these are all positive terms, so we didn't need to worry about absolute value. We did the ratio test. We did the limit as n approaches infinity of the n plus first term. That's the first parentheses, divided by the nth term, and we just multiplied by the reciprocal. And then we simplified. 3 to the n plus 1 over 3 to the n is 3. Then we pulled the 3 out and divided everything by the highest power of 5 to the n plus 1, and then found the limit. The limit was less than 1, therefore it converged. Everyone's good with that? Zoom, are you good with that or no?
All good.
29 of you that are here. We're missing 4 Zoom people today. Very, very bad. All right. Oh, here's a fun one. Okay, let's look at this one. The sum from n equals 1 to infinity of 1 over n times n plus 1. Try and find the sum, which means that it should converge. True? That's what we think. We think that it should converge. But anyway, find the sum. Well, we'll say this, or show it diverges, just to make our lives a little bit better. Not worse, I guess, actually. So in order to determine if it converges, what's the test that we've been using? The ratio test, right? Let's just for fun see what happens if we do the limit as n approaches infinity. These are all positive terms, right? All positive for all n. Okay, so as n goes towards infinity, we're going to look at the n plus first term, so that'd be 1 over n plus 1 times n plus 2, divided by 1 over n times n plus 1, which would give us the limit as n approaches infinity of, if I were to simplify that down, what? N over n plus 2, which is 1. And what is a limit of 1 in the ratio test tell you? No. But it's inconclusive. And so we're not sure. We think that it might converge because the original question just said find the sum. But our ratio test is inconclusive to determine if it's convergent or divergent. So it might converge, it might diverge. According to the nth term test for divergence, it might converge, it might diverge. Right? That limit is 0. So what can we do here with this? Oh, somebody. All right. Yes. So let's do the partial fraction decomposition of this. Is that what you're going to say now? No. That was your chance to say yes. Oh. Yes, you could have said yes, and then that would have been smart. You're too honest. Yes. All right. So we're going to do partial fractions here. We're gonna split this apart and see what happens with it. So what's that going to look like? That's going to look like 1 over n times n plus 1 equals, let's see, that'd be, we'll call it an a over an n plus a b over an n plus 1, right? So that'd be a n plus a plus b n all over that n times n plus 1, which we can then cancel out. And we're looking for the values of a and b. Our variable here is n. How many n's do we have on the left? 0. How many n's do we have on the right? A plus b. How many number constants do we have on the left? And on the right, it is a. So a is 1, b is -1. And this series then begins to look like the sum from n equals 1 to infinity of 1 over n minus 1 over n plus 1. Now, we could, because this is a series with all positive terms, isn't it? True? And it is decreasing. What test could we use to see if it converges? What's the test that's good for a continuous positive decreasing function? The integral test. We could use the integral test. The integral test, though, isn't going to tell us the value. It will show us that this converges, and we should be able to determine that it converges without, just by thinking a little bit about it, because the denominator is really 1 over n squared plus n. And if we were to compare that to 1 over n squared directly, right, 1 over n squared plus n is always less than 1 over n squared for all n values 1 and greater. Would everybody agree with that? Yeah. And in fact, let's just for fun write this out. 1 over n squared plus n is always less than 1 over n squared. Everyone would agree with that? Yeah, for n greater than 1, right? Greater than or equal to 1. Right? I mean, that's true. Everyone agrees? And what do we know about 1 over n squared? Yeah, 1 over n squared, this converges by p series, right? So what does this converge by? Yeah, this converges by direct comparison. So we know it converges. So that's good, right? We can prove that it converges, but the question is specifically asking us to find the sum if it does converge. And so we're going to have to use this idea right here, that this is 1 over n minus 1 over n plus 1. In this specific type of series, we call a telescoping series. Okay? And the reason why we call it a telescoping series is, let's think about the sum from n equals 1 to infinity of 1 over n minus 1 over n plus 1. Well, let's write the terms of this out, starting at n equals 1. The first term is 1 over 1 minus 1 over 2, which we know is a half, but I'm going to write it as 1 minus a half. So that's what we get from our series. What's the next term? At n equals 2, right, it's a half minus a third. What about the next term? Should be a third minus a fourth. The next term ought to be a fourth minus a fifth. And we would note that that pattern would go on forever. Okay? We call this a telescoping series because you think about a telescope, right? You were like a small child and you had a telescope and it came in like some small box, and then you like opened it up and put it together, and then you extended the telescope out into like this long telescope, and it collapses in on itself. Yeah, you guys are familiar with the telescopes that like collapse in on themselves and all that, right? So that's what this series does. Right? What happens to the minus a half and the plus a half? They collapse in on themselves, right, and cancel out. Same with the minus a third and the plus a third, and the minus a fourth and the plus a fourth, and the minus a fifth and the plus a fifth. What's left? 1. What else is left? The second part of the last term, right? So this becomes 1, and then that second part of that last term is a minus, right? So 1 minus the limit as n approaches infinity of 1 over n plus 1. Well, that happens to be 0, so we just end up with 1. So this series sums to 1. And it's called a telescoping series. Telescoping series is any series that sort of meets this criteria where the pieces inside of it will cancel each other out. Oftentimes you'll get these from partial fraction decomposition. They could come from other ways too. You could get like a logarithm that gets split into multiple different pieces, or all kinds of different things. So this is just another type of series to be aware of, called a telescoping series, and that you need to, when you do these, you need to see what cancels out, and then evaluate all of the pieces that will be left to find the sum. And usually that includes the first term, and the limit as you approach infinity of some part of the last. What I wrote there is perfect. It's good enough. You don't need to do anything other than that. You can, I mean, you could note telescoping, but beyond that, that's good. Any questions on that? Zoom?
Good.
Wonderful. All right. Next thing we're going to talk about is a test called the limit comparison test. This is one that we won't use as often as the ratio test, but we might use it at some point. Limit comparison test. Well, I'll let you guys read it. You guys are capable readers. You're all literate, right? Literate-ish. I'll let you read it, and then we'll talk a little bit about why it's true. Y'all ready to talk about this, or are you still, people here are still right? Yeah? All right. The limit comparison test assumes that you have two positive series, or at least series that are positive after a certain index value. Okay? Generally, it's just all of them. And if your series is not always positive, of course, remember that you can always just take the absolute value of it to make it always positive, and then deal with that later. So it says that if you take the limit as n approaches infinity of the nth term of one series and the nth term divided by the nth term of the other series, and it comes out to be some number between 0 and infinity, that will tell you that these two series are effectively growing at the same rate, meaning that they either both converge or they both diverge. If that limit comes out to be 0 and the one in the denominator converges, then that means that the one in the numerator also converges. Because if it comes out to be 0 and the one in the denominator is convergent, that means that the thing in the denominator is growing more quickly than the thing in the numerator for that limit to be 0. And so if the thing in the numerator is growing more quickly than the other thing, but it still comes to some number, well, then the one in the numerator must come to some number. And sort of the reverse of that is true if it comes out to be infinity, right? And the one in the numerator, if the one in the denominator diverges, then the one in the numerator also has to diverge. Meaning that the one in the numerator is growing more quickly than the one in the denominator. And if the one in the denominator diverges, then the other one must diverge, in fact, more quickly than the other one. So that is called the limit comparison test. You'll find that you might look at some of the series that we're going to deal with and say, I could have done that one using direct comparison. One of the issues that comes up, though, with trying to use direct comparison for some series is you have to find the index value for which the one series is always bigger than the other one. In the case of the limit comparison test, you don't have to worry about that. Right? It doesn't matter if if A or B is larger at any certain value. We're just looking at what happens at infinity. So it makes life a little bit easier than the direct comparison test does sometimes. Conceptually, do those ideas make sense about why each of those limits would mean a certain thing? Yeah? Okay. All right, cool. So let's take a look here at this series, 3 fourths, 5 9, 7 16, and so on. The sum from n equals 1 to infinity of 2n plus 1 over n plus 1 squared. And what we're going to do, similar to when we did the direct comparison, is we're going to look at the greatest power of n in the numerator and the greatest power of n in the denominator. So what's the greatest power of n in the numerator? 1, right? Just n, right? And in the denominator? N squared. So what we're going to do is we're going to simplify that down, n over n squared into 1 over n. And we're going to use this as our series that we're going to compare it to. Everybody good there? So we'll say, let me just say compare to this. Compare to 1 over n. And so what we'll do is we'll take our series and put it over 1 over n, and we'll look at the limit as n approaches infinity of 2n plus 1 over n plus 1 squared, all over 1 over n, which will effectively make this a limit as n approaches infinity of 2n squared plus n over, I'll just write it out, n squared plus 2n plus 1. And what is that limit? Should be really easy to find that limit. Should just be 2, right? It's just the horizontal asymptote of that rational function, right? It's just n equals 2, or sorry, it's just equal to 2, right? Coefficients, divide the coefficients since the degree of the numerator and the degree of the denominator are the same. 2 is a number between 0 and infinity, which tells me that either both of my series and the one I compared it to converge, or they both diverge. And so we will say the sum from n equals 1 to infinity of 1 over n diverges or converges? Diverges by the P series test. So the sum from n equals 1 to infinity of 2n plus 1 over n plus 1 squared also diverges by the limit comparison test. Good or no? At home Zoom people, okay with that or no?
Yeah.
Wonderful. Let's do another one. Okay. This one looks slightly different, I think. 1 over 2 to the n minus 1. Well, one thing I forgot to mention back there. What should we have noted here? If we're going to use the limit comparison test, I'm going to make sure we're being careful with all of this. All of these terms are all positive terms, right? So that's criteria that we need to have. Both 1 over n and 2n plus 1 over n plus 1 squared have all positive terms. So once again, you can always take the absolute value if you need to, but nice when you don't have to. All right, what about this one? 1 over 2 to the n minus 1. So 1 plus a third plus a seventh, and so on and so on and so on. First thing we should check is, are they all positive terms? Are they all positive terms? For n equals 1, that's 1 over 1. For n equals 2, that's going to be 1 over 3, right? So there's never going to be negative terms, right? We're going to say this is all positive. What do you think we might want to compare to? Anybody have a suggestion? One over 1 to the n is just 1 over 1. That's just 1 plus 1 plus 1 plus 1. That doesn't seem good. Nobody has a suggestion on this? 1 over what?
1 over.
I don't know what you're saying.
It's like 1 over 2 to the n minus 1. Or 1 over.
Well, we have 1 over 2 to the n minus 1.
Or like take the exponent. The n minus
Oh,
1.
I see what you're saying. You want to, I see. Let's see what this is. All right, we have 1 over 2 to the n. 1 over 2 to the n. Let's go with that. Somebody said that in the chat. Let's go with 1 over 2 to the n. Yeah, you usually don't want to change the power. So like if you think about the last one, we didn't change the power, right? The effective power here was 1 over n, right? With an n to the negative 1 in the denominator. Same thing here. We don't really want to change that effective power. So well, let's think about 1 over 2 to the n. First off, it's all positive, right? So that's good. So we can use that. Let's find the limit. Let's do the limit as n over, or the limit as n approaches infinity of 1 over 2 to the n minus 1 over 1 over 2 to the n. And what do we end up with then? We end up with the limit as n approaches infinity of 2 to the n over 2 to the n minus 1. Well, we should probably have a pretty good idea of what that limit is, but how could we prove that limit? I mean, technically it's infinity over infinity, right? So that's a problem. How do we deal with infinity over infinity? We can use L'Hopital's rule. What's the derivative of 2 to the n? No. You should know the rules for a to the x. What? No. No.
2 to the natural log of 2 times 2 to the n.
2 to the n times the natural log of 2. Yes. And what's the derivative of 2 to the n minus 1?
Same thing.
2 to the n times the natural log of 2. And what happens if you have the same thing divided by itself? That's 1, right? This just becomes the limit as n approaches infinity of 1, which is 1. What can you tell me about 1? 1 is less than infinity, greater than 0. So they either both converge or they both diverge, right? Everybody agree with that?
Yeah.
But we didn't make any grand statement about the sum from n equals 1 to infinity of 1 over 2 to the n, about whether that converges or diverges. Do we know if that converges or diverges? So we picked a series, right? Kevin said, pick that series. So we picked that series. We could try to do the integral test for that one. That's true. We could do something easier.
It's geometric. So
Yes, wonderful. So the sum from n equals 1 to infinity of 1 over 2 to the n, right? I mean, if you think about that, that's just a half plus a fourth plus an eighth plus a 16th and so on. Right? This is geometric with a common ratio of 1/2. Absolute value of 1/2 is less than 1, so it converges. So by the limit comparison test, the sum from n equals 1 to infinity of 1 over 2 to the n minus 1 converges. Even though a series of 1 over 2 to the n minus 1, I mean, that series is always going to be always going to be greater than the series of 1 over 2 to the n from n equals 1 to infinity. Every single term is greater than it. We were still able to use 1 over 2 to the n, the smaller series, to show that they both converge. Good or no? Yeah, good. We're good. All right. I want you guys to try and do this one on your own. I'll give you guys 2 or 3 minutes here to work through this one. Okay, so first off, are all the terms of this positive, starting at n equals 2 and getting larger than that? Yeah, all positive terms, right? And what are we going to compare it to? 1 over n squared, which is also all positive. All right, and we could even make a statement right here, converges by p series. So that if we end up getting something that's between 0 and infinity for our limit, we already will then know that this also converges. Everybody good there? All right. So limit comparison test, limit n approaches infinity of this series 3n plus 2 over n cubed minus 2n. And then we're just going to multiply by the reciprocal of 1 over n squared just to make life a little easier. Gives us a 3n cubed and an n cubed. That limit should be 3. So the sum from n equals 2 to infinity of 3n plus 2 over n cubed minus 2n converges by limit comparison. Easy enough? Yeah, everyone's good there? All right, let's do another one. We'll do this one together. Everybody at home okay with that?
Yep.
All right, let's look at this one. See if we can figure out if the series sine of 1 plus sine of a half plus sine of a third converges or diverges. Okay. It is not positive for all n. That's the first thing that Noah here says. So we'll say not all positive. That's okay, though. How can we deal with that if that's a thing? We're going to take the absolute value of it, right? So we're going to look at the sum from n equals 1 to infinity of the absolute value of the sine of 1 over n. And what do you want to compare that to? Anybody have a good idea on something to compare that to? In fact, can we go back a second here? Noah said that's not all positive. And I just tacitly accepted that. This is all positive. If you think about that, any value that you plug in, if we plug in any value of n here between 1 and infinity, right? Starting at sine of 1 is an angle that is less than pi over 2. It's in the first quadrant. The sine of something in the first quadrant is positive. And then if you plug in a 2, you're going to still be in the first quadrant. Plug in a 3, you're still going to be in the first. It's just getting smaller, going towards 0, staying in the first quadrant the whole time. So these are signs of all angles that are all in the first quadrant. Those are all positive. I shouldn't have accepted Noah at his word there. All positive terms. All right, so we'll just do the sum from n equals 1 to infinity of sine of 1 over n divided by what? What are we going to compare it to? Yes, we've got a good suggestion there. 1 over n. Right, we're going to compare to 1 over n. And this is another thing that you will note that oftentimes, if you have like some other non-regular algebraic function here of something 1 over n, right, of some argument of that here. Generally, the series you want to compare it to is that argument if it's something that you know how to deal with. And we know how to deal with 1 over n. We know that 1 over n diverges. P series test, or because it's the harmonic series, as you call it. We've called it the harmonic series before, right? No, the sum from n equals 1 to infinity of 1 over n is called the harmonic series. Okay, cool, good, okay. So sine of 1 over n over 1 over n. And shouldn't have this over here. We just need to limit as n approaches infinity, right? That was from before when Noah tried to tell me the wrong thing, and I tried to listen. Teach me to listen to my students. All right. So the limit as n approaches infinity of sine of 1 over n over 1 over n. How do we deal with that? What? No, because that'd be the limit as n approaches 0. We got two good options here. Right. So what could we do with that then? If I just make that n sine of 1 over n, though, then I have 0 times infinity, which is indeterminate. Yeah, I mean, we have, like I said, we have two options. What? One option is L'Hopital's rule. This is sine of 1 over infinity, so sine of 0, which is 0, over 1 over infinity, which is 0. So this is 0 over 0. That's one option. We could use L'Hopital's rule. The other option is we could just do a u substitution on it. We could let u equal 1 over n. So you'll note that either way, yeah, we got a u equals 1 over n there. So that's one option. U equals 1 over n, which just makes this the limit as u approaches 0 of sine u over u, which we know to be 1. The other option was we could have, if we wanted to, we could have used L'Hopital's rule. That would just give us the cosine of 1 over n times the derivative of 1 over n, which is negative 1 over n squared, and then derivative of 1 over n, which is negative 1 over n squared. The negative 1 over n squared would cancel. You just have cosine of 1 over n, which is cosine of 1 over infinity, which is cosine of 0, which is also 1. So either way would have been good. U sub or L'Hopital's, doesn't matter. But anyway, 1 is less than infinity, greater than 0. So the sum from n equals 1 to infinity of sine of 1 over n diverges by the limit comparison. Good or no? Any questions?
So are we often just dealing with like the first, I guess, rule of the limit comparison test?
Yeah, the majority of times that's what will happen. Yeah, it'll come out to be some finite limit.
This might be a dumb question, but do we usually have to mention the P-series test when we're doing this? Because one is between 0 and infinity, and then so would we have to mention P-series all the time on the AP test or on your quizzes, or if we just said?
If you say that it diverges, if you said this diverges by the limit comparison test with 1 over n, you need to tell me why 1 over n diverges.
Okay, cool, thank you.
Yeah, always specify why whatever you're comparing to diverges or converges, and always specify by what you're, yeah. Always give a reason. Always give a reason from one of the tests. All right. Cool. This is nice and easy. This is much easier than, not that the limit comparison test was difficult, but much easier than that. The alternating series test just says that a series will converge if these three things here below are true. One is that it alternates. Okay. So that's what each u sub n is positive. I have a positive term followed by minus another positive and plus a positive and minus another positive. So it alternates. Okay. And that the terms are getting smaller eventually after some index, capital N. The terms get smaller. U sub n plus 1 is less than or equal to u sub n. And if the limit as n goes towards infinity of the nth term is 0. So if all three of those things are true, if it alternates, gets smaller, approaches 0, then it converges. And so this is called the alternating series test. The alternating series test says if the series alternates, gets smaller, approaches 0, it converges. Simple enough? Another test. I think this might be the, no, there's still one more test we have to do after this one. But at least one, maybe two. But easy enough test there, right? Yeah. Alternates, gets smaller, approaches 0, then it converges. All right. So let us prove that the alternating harmonic series is convergent, but that it is not absolutely convergent, meaning that the absolute value of it does not also converge. Then we want to find a bound for the truncation error if we were to approximate the value of that series after 99 terms. So the alternating harmonic series. So I just mentioned a minute ago that the harmonic series is the sum from n equals 1 to infinity of 1 over n. So the alternating harmonic series is the sum from n equals 1 to infinity of -1 to the, well, we can't do n, we could say n plus 1 or n minus 1, either one. Or we could start at 0. Well, actually, we couldn't start at 0 because we'd have to have an n behind it. So -1 to the n plus 1 over n. This is the alternating harmonic series. So number one, prove that it is convergent. Okay, great. How do I prove this converges? Well, number one, does it alternate? Yes, it alternates. Number two, do the terms decrease? Yes, the terms decrease. Starting at n equals 1. Every term after that is smaller, right? And 3, the limit as n approaches infinity of -1 to the n plus 1 over n is 0. So this converges by the alternating series. If we were to take the absolute value of this series, what does that give us? That's just 1 over n. This diverges by the P-series test. And in fact, you can write on the AP test, if you use 1 over n, you can say it diverges by the P-series test, or you can just say it is it's the harmonic series which diverges. It's probably better to write P-series test, but you might get somebody that gets angry at you for that, that's tired on their last day of grading AP tests. But all right, so quick terminology thing. If you have a series that converges but is not absolutely convergent, we call that conditionally convergent. So like we said before, if something's absolute value converges, it converges, but the converse of that's not true. Right? If the series converges, that does not necessarily mean that the absolute value of that series converges. Right? The absolute value converges, the series does. The series converges, the absolute value may or may not converge. In this case, the absolute value of it does not converge because it's the P-series test in phase. So in that case, if something is convergent but not absolutely convergent on a certain interval or just in general, we call it conditionally convergent. And what we will be doing tomorrow when we finish up our last little bit of series stuff, we're still going to do a little more today, but what we're going to do tomorrow is we're going to take a power series, and I will say, find the interval of convergence, the radius of convergence, when it is absolutely convergent, and when it is conditionally convergent. And so you'll have to sort of investigate all of those many different things. And that is commonly what will be asked of you on the series free response question, or one of the parts of the series free response question. I believe I posted the series FRQs. Did I post them? Yes, yes, yeah. Hopefully you've started to sort of look through them. Yeah, it's almost always, I mean, it's basically, it's always question number 6, last pre-response question on the AP test. Anybody have any questions so far for today? We good? All right. So here are some things I would like you to think about momentarily. All right. Number 1, if I have a finite sum, can I rearrange the terms? Does that affect the value of it? I should be able to rearrange them, right? If I have something like 2 plus 3, 2 plus 3 plus 4, right? I should be able to rearrange those. That's the same thing as 2 plus 4 plus 3. Same thing as 4 plus 3 plus 2, and so on. You learned that many years ago when you were a small child. Yes? That addition is commutative. Yeah, you remember that. You remember the property. That's great, Derek. Addition's commutative. Yeah. All right. What about, let's extend this a little further. Can I rearrange some number of terms, any number of them, just as long as a finite number of them, 100 terms, or 72 terms, or 1,000,000 terms of an infinite series without changing the sum? I should be able to, right? I mean, as long as, you know, I take those 1,000,000 terms and I put them in any other order, well, the rest of the terms are still the same. And as I go towards infinity, I should still be approaching the same value. Do you all agree with that? So the answer to this one was yes. The answer to this one was yes. What about rearranging an infinite number of terms of an infinite series? Can I do that without affecting the sum? Meaning what? Noah says it depends on the pattern in which you rearrange it. Yes. But would that change the sum of it? You don't think it. So your answer is yes, you can. So your answer is yes. Okay. Noah says yes. You can rearrange an infinite number of terms. I could take as many of them as I wanted to and rearrange them in some other order, and it should come out to be the same value. No. Woman walk. Woman walk today. No man walk. Woman walk today. Those weird people walking around. All right. Let's take a series that we just dealt with. The series 1 minus a half plus a third minus a fourth plus a fifth minus 6 and so on. What is that series? It converges. Okay, we know that series converges to a sum. So sum. Everybody agree with that? Yeah. Now, what I want to try to do is I want to try to rearrange the terms of this so that it equals something else. See if I can do that. All right. So what I'm going to do is I'm going to make this series. I'm going to make this series equal 1. What is, actually, let's start with this. What does this series equal currently? You should know what this series equals. We've talked about this series a few times already. No, not 2. It's got a 2 in it. It's not 1/2. There we go, Ryan. Yes, this is the natural log of 2. All right. Now I'm going to make this series instead of having this series equal the natural log of 2. I'm going to make this series equal 1. Just for fun. Okay? I'm going to start with 1 minus a half. Am I less than 1 right now? I am less than 1. Everybody would agree with that? Now I'm going to add the next positive term. I'm going to add 1/3. I haven't rearranged anything yet. True? Nothing's been rearranged. Am I above 1? Am I below 1? I'm below 1. All right, what if I do this? Am I above 1 or am I below 1? Oh, sorry. That's a positive. Sorry, I meant to be a positive. Am I above 1 or below 1? I'm now above 1, right? I've done 1 minus half, which is a half. I've added a third, and I've added a fifth to that, which is 8/15. So I've added more than a half to it. So I'm now above 1. Did y'all agree with that? Okay. Now I'm going to subtract a 4. Am I above 1 or am I below 1? I'm below 1 again, right? Okay, so now what I'm going to do is I'm going to continually add more terms. I'm going to add my 1/7. That's not going to get me back above 1. If I add my 1/9, I don't know, is that going to get me back above 1? Somebody evaluate that real quick. Is that going to get me above 1? So here, and I'm going to make a note here. Here we are less than 1. Here we are greater than 1. Here we are, I'm back above 1. Okay. And then I'm going to, for 1 second, then I'm going to subtract, let's see, what's the next one I need to subtract? 1/6. Am I back below 1? And then if I add an 11th, am I above 1? No. What if I add an 11th and a 13th? Back above 1? And I could continue doing this. Let's see, next thing I do is subtract an 8, right? And then I would add a 15th, and I would add a 17th, and then maybe a 19th until I was back above 1. And then I could subtract something until I was below 1. Then I could add some more terms until I was above 1. And then I could subtract a term until I was below 1. And then I could continue adding more terms until I was above 1. And would I ever have to stop doing this? I could continue doing this. And what would the values of my series be getting closer and closer and closer to? They'd be getting closer to 1. This series would now equal 1 if I did this infinitely. So I have rearranged an infinite number of the terms in this series to create a brand new sum for it. Could I do this with any value I wanted? Could I add 1 plus a third plus, a fifth till I was above, let's say, I don't know, till I was above 2, and then subtract a term to be below 2, and then add a bunch of positive terms till I was above 2, and then subtract a term till I was below 2, and then continue. Or I could subtract a bunch of terms till I was below 0, and then add a term to go above 0, and then subtract terms till I was below 0, and then add a term to go above 0. And I can make it equal 0. We should be able to make this series approach any value that we want it to approach. So can you rearrange it? Not necessarily. Yeah, but then you were like, actually, we just do it, and we could, and something like that. So the answer is not necessarily. If it alternates, there is the ability to make that series approach any other value that you want it to. And in fact, we could also make this series diverge if we wanted to. How would we make this series diverge? Well, we can't add all the positive terms first because there are an infinite number of positive terms. So we would never get around. But we would never get around to, we would not have the same series because we never get around to putting in any negative terms. So you've eliminated half of the terms. Nope, not at all. I haven't eliminated any terms.
after, like, there are less negative terms you will get to after a certain value. After infinity, you will get full value.
What do you mean after? And what do you? I'm sorry. Noah just said after infinity, and I'm going to now question him. What do you mean by after infinity? Infinity is not a concrete value. There's not, it's not a finite concept. That's why it's infinite. It's not a finite value. I cannot go beyond infinity. Infinity is infinity. It goes on forever. I must be able to continue putting all of these terms in forever. Kevin, to answer your question, yeah, that's what I said there. If it alternates, it's possible to do this. Yeah, you can only rearrange the terms if it's absolute. If it's absolutely convergent, yes, then you should be able to rearrange them. That is correct. It is not absolute. We just proved a minute ago that it was not absolutely convergent. That's why I picked this one. For an absolutely convergent alternating series, absolutely, let me think about that. That's whatever. Yeah, for an absolutely convergent alternating series, you should still be able to rearrange them and get a new sum. Just doing the exam. I mean, if you think about something like 1 over n cubed, right? 1 over n cubed is absolutely convergent, but it is. No, that's never mind. No, sorry, I didn't mean 1 over n cubed. I mean -1 to the n plus 1 over n cubed. That's still absolutely convergent, but you should still be able to follow the same process. So it should still be possible to rearrange them. So only if you have an alternating series will it really work. But if it is absolutely that's never possible now. Sorry, I got a little sidetracked. So Kevin, I'll answer your question in a second now. So Kevin, to answer your question, if the series is absolutely convergent, let's see, if the series is absolutely convergent, but it still alternates. Yeah, you should still be able to. So you should still be able to rearrange them without affecting the sum, because even if you have some negative terms in there, that's Noah was just asking, like, you know, is there ever like you run out of terms to go beyond it? Well, that's what happens with an absolutely convergent alternating series, is that you would run out of these terms. So if the series is conditionally convergent as well as an alternating series, and it would have to be an alternating series for it to be conditionally convergent, because if it's not an alternating series, if it's all positive terms, then it's just going to be an absolute, you know, the convergence will be absolute convergence as well. So only if it is alternating conditionally convergent. And then Noah, your question was, couldn't it go? Yes, yeah, if it alternates and conditionally converges, I'll add this conditionally converges to be more specific. So your question was, for example, in this series, just in a series that is absolutely convergent, yes, it is. The answer is yes. If it's absolutely convergent, the answer is yes. Yeah, so that's what I was going to say. So for this, I mean, I've just used this particular case, but for this particular case, yes, that is, yeah. I mean, I already had it written there, so I didn't erase it. But yes, you are correct, Kevin. It is redundant to have it say that it alternates and it conditionally converges. Because if it conditionally converges, it has to alternate. Anyway, what was I saying, Noah? What was your question? For this, I'm going to use this as a case. We know that there's never going to be a certain number of of values in there where I can no longer go beyond 1, because if you think about it, if you just look at like the series 1 over let's just take the negative ones, like negative 1 over 2n is effectively what this is, right? Negative 1/2, negative 1/4, negative 1/6, negative 1/8, and so on. That series diverges. That will continue getting smaller and smaller and smaller forever. Same with 1, 1/3, 1/5, 1/7 positives. That will continue getting larger forever, just based on the p-series test. And so because of the p-series test, those series each diverge, telling you that no matter, eventually I am going towards infinity when I add those terms up. 1 plus a third plus a fifth plus a 7 plus a 9 plus 11 goes towards infinity. Right? That equals infinity as you sum them together. And so therefore, as you add more terms into it, you will always be able to get above whatever value you want to get above. Does that make sense? And subtracting, you will always be able to get below. There's always enough terms because that series does not converge to a specific value. Correct. But it's not just that you have an infinite number of positive terms and an infinite number of negative terms. It's the fact that the series of just the positive terms goes towards infinity, and the series of just the negative terms goes towards negative infinity. So, an infinite values work. Yes. Okay. Yeah. Correct. Yes. That makes sense. Yeah. Good. We could, in fact, like I was saying, we could also turn this series into a series that diverges. So I could make this a series that diverges by saying, let's start with 1, and then we'll subtract a 1/2, and then we'll subtract, let's see, a 4, and then we'll subtract, well, let's just subtract, yeah, that's fine, just subtract a 4. If I do 1, perfect. If I do 1 minus a 1/2 minus a 4th, I am below a value of 1/2. Would you all agree with that? I'm now going to add a 1/3, and I'm going to add a 5th, and let's see, let's add a 7th. I don't know, we're going to add enough terms so that here we are below 1/2, and here, I hope, we are back above 1. Probably that's true. Then we would just subtract more terms. I don't know how many it takes to be less than a 1/2 again. Then I would add some more terms until I was greater than a 1/2. And then I would subtract a bunch of terms until I was less than a 1/2. And I should be able to do that infinitely, just like I was able to go above 1, below 1, above 1, below 1. But here, I'm now oscillating between eventually being above 1 and then below a 1/2, and then above 1 and then below a 1/2. And so there's no specific value that I would be convergent to. So in fact, we can rearrange an infinite number of these terms in the infinite series to get any predetermined value that we would like, as well as to make it be a divergent series. Not that it's going towards infinity, but just that that series diverges because there's no specific value that it's approaching. Does that make sense or no? Those of you in the Zoom, does that make sense or no? Kevin, to answer your question, remaining tests we still need to talk about. I think there's just one, is the nth root test, I believe, is the last one we're going to talk about. I think that's the last one. Yep, that's the last one because I don't have any more in here. The nth root test is the last one we're going to talk about. All right, that's it for today.